Hello friends, welcome back to the lecture series on applied statistics and econometrics. So today we are going to continue our discussion on hypothesis testing, and we are going to look at couple of new tests. So let's have a look at today's agenda item. So in today's lecture we are going to talk about a very useful test called Pairedt t-test. Then we are also going to look at the other variations of two sample tests, namely proportion and variance tests, and finally we will end our discussion by briefly discussing a very interesting concept called Cramer's V. So our first topic is Pairedt t-test. So what does it do actually, if you want to describe it in simple language. So sometimes we study the same group of subjects or elements in repeated samples, and we may be interested to see how the mean is changing from one sample to the other. So here, as elements in one sample is matched with the element in another sample, that is why it is called the paired sample or matched sample, and we are going to now describe the t-test which could deal with this type of samples. So in many research designs it is required to measure the same people more than once. So here is an example. Suppose manager of an office or your boss, he has decided to send some staffs for training so that they can improve their typing speed. So before he sent his staff to the training, the typing speed was recorded, and then after the training, when the person rejoins the job, again the typing speed is recorded. So if you send some 10, 15 or 20 staff for the training program, so there is a before training mean typing speed, and then there is an after training typing speed. So you may be interested to see whether there is any improvement in the overall mean typing speed for this group of staff. So here you have to apply Pairedt t-test, and now I am going to briefly discuss about some features and assumptions. So I have already mentioned these features, that observations in the sample are paired as they can be matched across the sample. So that is we have discussed. Now let me state the assumptions clearly. So we assume that population ideally be normally distributed. If it is not normally distributed, then at least large samples are required, and then you assume that there are n pairs in the matched or related sample. So it is better that you have n greater than or equal to 30. So to conduct the test, the first step is to compute the difference, and this is for the ith sample member. So here I define this difference as di as x1I minus x2I. So x1 and x2 are basically two different groups. So suppose this typing speed is the variable. So 1 is basically after the training and 2 is before the training, or you can think of several other examples, but I is basically common. So that is basically the ith sample member who is common in these two groups x1 and x2. So then how do I define my point estimate for the population mean paired difference? So here is the formula. So d bar is the notation that I am introducing here as the point estimate, and that is basically nothing. You have to take the arithmetic mean of that variable di. Now in the next step you have to frame hypothesis as usual. So here I start with the null hypothesis that there is no significant difference between the averages of the two sets of sample, and then I say that okay, my H naught can be represented as mu d equal to 0. So d is basically the difference variable that I have created, and mu is basically the population mean. Okay, now alternative hypothesis can be set in three different ways, So, here we define the alternative hypothesis as there is significant difference between the averages of the two sets of sample, and there can be three types of mathematical form that one can assume. So, first one is going to give you a left tail test where you write alternative hypothesis as mu d less than 0, and the second type could be the right tail test, and there you write your alternative hypothesis as mu d is positive, or you can have a two tail test where you can write H1 as mu d not equal to 0. So, now in this case you have to define the test statistic as the next step, and here is the test statistic, that is basically a z score, and then you have d bar, that is the sample mean of the difference variable d, and then you have to take the difference between the sample mean of d and the population mean mu d. So, if you work with the above shown null hypothesis, then mu d will of course take value 0 when you compute the test statistic, and this difference now shall be divided by the sigma d divided by root n. So, the sigma d is of course the unknown population standard deviation, and most likely it will remain unknown. So, then what to do? So, you can actually get a proxy for sigma d, and the proxy could be defined as the sample standard deviation, which is defined as S d, and I am showing you the formula in the red box, and that is not uncommon to you. You have seen how one can compute the sample variance. So, we are using the same formula, only in the place of x's now we are writing d's. So, once that SD is computed, in the next step you write the expression for the new statistic, and that is a t statistic, and I am showing you the expression in the box, and this will follow a student's t distribution with n minus degrees of freedom, and then you follow the decision rules valid for the t test that we have discussed before. It may also be interesting to go for a hypothesis testing for population proportion. So, sometimes it is interesting to compare the population proportions that come from two different populations. So, you may get a sample from population 1 and you may get another sample from population 2, and you look at the sample proportion, they look different to you, but are they statistically different? That could be an interesting research question. So, in the next hypothesis testing we are going to discuss this particular issue. So, we begin by introducing some notations. So, let two population proportions are pi 1 and pi 2, and then I define something as p bar, that is a new thing that we are defining in this course, and that is basically a weighted average of the sample proportions. So, here if I am dealing with two groups, group 1 and group 2, the sample proportions are p 1 and p 2. So, what is p 1 and what is p 2? So, if there are x 1 number of elements satisfying some criteria out of n 1 sample in group 1, then p 1 is defined as x 1 divided by n 1, and similarly one can define p 2 as well. So, now as there are n 1 and n 2 number of observations in two different groups respectively, you take weighted average, and then you get the overall sample proportion p bar, and then once that is calculated, you now define your point estimate for the difference, and now you define that to be p 1 minus p 2, and next you decide on the test statistic, and then you have the complicated z formula. Well, it may look complicated initially, but it is not, because if you recall certain things from the previous lectures, it is very common thing that we are still following here even in this particular slide. So, when you actually write a test statistic, you have to in the numerator you have to first talk about the difference between the sample statistic and the unknown population parameter value. Okay. So, here P1 minus P2 is basically that point estimate, that is basically as a statistic you can assume, and then pi 1 minus pi 2 is basically the unknown difference between population proportions pi 1 and pi 2. So, the same philosophy is or the concept is applied here in the numerator, and in the denominator what are we seeing? So, if you remember, the variance of a proportion is basically p times 1 minus p divided by n, that we have seen earlier. So, now p is unknown. So, we have to get a proxy measure for p from the sample, and that is basically your p bar, the overall sample proportion. So, basically now you have two different sample sizes n1 and n2. So, you see the term that you are seeing under the square root, that is basically the combined variance of two different samples. So, of course, here also we can see that there could be three different scenarios. One is lower tail or left tail test, one is upper or right tail test, and there could be one two tail test. So, here first we are going to talk about the lower tail test, and I am showing you how you can write the null and alternative hypothesis. So, nothing new here. Similarly, one can frame the null and alternative hypothesis for the upper tail test, nothing new here as well, and then finally you have the two tail test. And you have to first decide which particular test you want to conduct. So, accordingly you frame your hypothesis, and then after that you have to conduct a standard Z test, because here your test statistic is Z, and as you are assuming that you have large sample. So, n1 and n2 ideally is greater than or equal to 30. So, you can actually conduct a Z test. So, now we are going to discuss the case of F test. We have not seen F test before. So, we are going to introduce this concept for the first time, and you will see later on in the course we will find very nice applications of F test. So, in the next slide I am going to show you the fundamental steps of conducting an F test, and I am not going to get into details of statistics regarding the F test. I am just going to talk about the most important things. Okay, so let me first introduce the F test in the most simple possible language. So, it is a test for which the test statistic follows an F distribution if the null hypothesis is true, and famous statistician Ronald A. Fisher actually first developed this statistic as the variance ratio. If you remember, the way I defined the F value and the F distribution while I was talking about the children of the normal distribution, then it was the ratio of the variances, and that was the form that Ronald Fisher introduced, and in his respect this distribution finally was named F distribution. So, there is another interesting feature that in most cases the F distribution is a positively skewed distribution, but the shape of the F distribution is going to change, because F is a very complicated distribution. It has 2 degrees of freedom. Remember, in the chi-square case we had 1 degrees of freedom. Now, here we have 2 types of degrees of freedom, because it is a ratio random variable. So, for the numerator there is 1 degrees of freedom, and for the denominator there is another degrees of freedom. So, the shape is determined by dfn, which is the degrees of freedom corresponding to the variance in the numerator, and the dfd, which is corresponding to the variance in the denominator of the ratio of two variances. So, at the bottom part of the slide I am going to show you a small diagram, a simple diagram where I am showing you various cases of FPDF. So, here you see the pink one, which is looking almost like a rectangular hyperbola, is FPDF for dfn equal to 1 and dfd equal to 8. And you see, if I now increase the DFN and DFD values to 3 and 11 respectively, then I get this orange colored PDF shape, which is a typical positively skewed distribution. And if I continue to increase the DFN and DFD values to 8 and 26, then I get a PDF of higher height, and it has got higher density in the right tail also, and that is given by the green colored PDF curve. Okay. Now, I am going to tell you here about one statutory warning, or you can see that as a cautionary note. So, when you are referencing F distribution, when you are trying to get the critical values from an F table, then DFN, or the degrees of freedom corresponding to the numerator, is always given first. So, you have to look at the column first, and once you fix the column for the numerator degrees of freedom DFN, then you have to come to the row for DFD, which is basically the degrees of freedom for the denominator. And this is very important. Why? Because switching the order of these DFN and DFD will have a big impact on the shape of the distribution and the corresponding critical values and probability values. Now, in this context of F distribution, let us look at the very important concept of p value once again. So, here now let us concentrate on this diagram again, and now we are going to talk about a specific value of f, which is the calculated value of test statistic, and let me denote by f star. So, now you erect a vertical line or draw a vertical line on f star, and then of course, it will partition your probability density function into two parts, one in the right hand side and one on the left hand side. So, now when you concentrate on the area of right hand side right with respect to f star, then basically that area below the f PDF curve gives the p value. So, how do I interpret this p value? So, here in this context, it is the probability of getting a test statistic at least as extreme as f star if the null hypothesis is true. Now, we are going to look at one example of F test, and that is basically when we want to compare two population variances. We do not know the true values of the population variances, but we want to draw some inference based on the sample variances. So, how do you conduct a statistical testing to solve this problem? So, here a two sample F test is used to compare two population variances when a sample is randomly drawn from each population. Here we have to make a very strong assumption that the populations must be independent and normally distributed. And if you remember our previous lectures, the F test could be of three types here, one of the three types, and they are namely left tail test, right tail test and two tail test, and I am showing you the null and alternative hypothesis under both categories. So, you see these expressions are given in these three boxes. So, the left hand box talks about the left tail test, and you see sigma 1 2. These are the notations I am using to denote the population standard deviations for population 1 and population 2, and if you follow that notation, then of course these expressions are easy to follow. And then in the center I have right tail test description of null and alternative hypothesis, and finally at the right hand side the third box gives me the null and alternative hypothesis for a two tail test. Now, the question is that we do not have any a priori knowledge about the population variance values. So, we do not know sigma 1 square and sigma 2 square. So, then how to proceed? We have to draw a sample and we have to calculate the sample variances from these two samples, and let me call them S1 square and S2 square. So, after calculating S1 square and S2 square the sample variances, most likely we are going to see that one of these is higher than the other. So, you call that higher variance corresponds to the population 1. So, you name that population as population 1, for which you observe the highest value or the higher value of sample variance, and so we can write S1 square is greater than S2 square. This is important to conduct an F test for checking the difference in variances. Now, it is time to look at the degrees of freedom issue. So, if you remember that when we are conducting F test through F distribution, it has 2 degrees of freedom, one is associated with the numerator and the other one is associated with the denominator. So, let us have a look at them, what they are. So, here dfn is n1 minus 1. So, that is basically the number of observations in sample 1 minus 1, and dfd, that is basically corresponding to sample 2, and it is defined as number of observations in sample 2 minus 1. So, I am not going to give you sentences where I am typing what to do next, what to do next. So, here I am going to take a graphical approach to explain how to conduct an F test. We already have spoken about that diagram 2 slides before. So, you will see a practical application of that slide again here in this slide, where I am going to describe this F test procedure again. Okay, so this slide will start by calculating the test statistic value. So, we have to define the test statistic first. So, the test statistic is defined as capital F, and that is ratio of the sample variance from population 1 and sample variance of population 2. So, remember here that population 1 is that population where the sample variance is higher when you compare two sample variances. Right. So, that is what we have written, and this particular test statistic follows an F distribution with 2 degrees of freedom, namely n1 minus 1 and n2 minus 1. So, I have actually explained them the previous slide. So, next you have to set the level of significance at alpha, and then you need to set the decision rule. So, for a particular level of alpha, as the degrees of freedom are given for both numerator and denominator, it is not a difficult task to get the critical values Fu and Fl. So, Fu is basically the critical value for the right tail, or it can be called critical value of upper tail, and correspondingly we can find Fl, that is basically the critical value for left tail or the lower tail, and that is denoted as Fl. So, now I set a decision rule that if the calculated value of F is greater than Fu, then you can reject your null hypothesis, or if the calculated value of F is less than the critical value Fl, then also you can reject your null hypothesis. So, that is basically shown here in this diagram at the left hand side and the bottom part of the slide. So, here it is basically the same diagram that I have shown you maybe a couple of minutes back, but here I am indicating the rejection regions again corresponding to or relative to Fl and Fu, the critical values, and then the task at hand is to get the Fl and Fu. In that case you will be able to take a decision for this sample test. Now, finding F values from statistical tables is a very challenging task. Why? Because for a particular level of alpha you have 2 degrees of freedom. So, when you think about that matrix form of the F values, so in row you will have one set of degrees of freedom values, and on the columns you will have other set of degrees of freedom values. But note that that matrix structure or the table will be valid for one particular alpha value. If you change alpha, then again the same table will be reproduced, but with different numbers in the cells as you have changed the alpha value. So, F table, it is very difficult to give you the entire picture in one slide. I am going to show you glimpse of one particular F table for one particular level of significance, but there are many textbooks where you can find the longer versions of F table, or you can use software or online calculators to find the critical values or the probabilities in the F table. So, let me now take you to a short glimpse of a particular F table. So, here I set alpha value at 0.05, and here the rows show the critical values of the denominator degrees of freedom. So, DFD, and the columns show the critical values for the numerator of degrees of freedom. So, it is basically DFN. So, as I told you 2-3 slides before that, you have to first look at the column, and then you have to come down rows, and then you have to refer to the denominator degrees of freedom. So, that is the way you have to read the table, but this is the table for right tailed test, right. So, if you now have to conduct the two tail test, how do you proceed? It is actually not very simple. So, I am trying to express this in words. So, now look at the bottom of the slide. Here I have written 2 steps. So, in step 1 you have to first identify FU from the F table for n1 minus 1 numerator and n2 minus 1 denominator degrees of freedom. Okay. And then in step 2 you have to find the FL, the critical value at the left tail, by using a formula, and that is given by FL equal to inverse of FU star. Now, this FU star is not the FU that you have computed in step 1, this is somewhat different. So, what is it? So, here the FU star actually is to be found from the F table with n2 minus 1 numerator and n1 minus 1 denominator degrees of freedom. So, you have to basically switch the degrees of freedom from the calculation of FU. So, we are going to end today's discussion. I thought to cover Cramer's fee in today's lecture, but I had a second thought, and I think that I will cover that concept in the lecture on the relationship between variables. So, wait for the next lecture. Thank you.